Cmax is the maximum cell concentration up until which cells are metabolically active, and the genetic circuit or the reaction can function. This basically allows us to capture the fact that in a growing colony, only the periphery is metabolically active, while the center enters in stationary phase and it becomes metabolically frozen, which is the mechanism with which concentric rings are created in a colony harboring an oscillator. The initial inoculum of our colony is represented by two parameters, height and width. Height corresponds to C0 colony, which is basically the coefficient of a two-dimensional Gaussian function centered in the center of the simulation grid. So basically the height of that Gaussian function. In case your initial inoculum has a very spatial shape, you can even change this function in the accessory function folder. Then colony width has the same unit as the Ly length. So if we set colony width to 100, it means that our initial inoculum will already be as big as the entire simulation grid. So to start, we can maybe set something between 10 and 100 times smaller than Ly. Then the growth of the colony will be described by a Fisher equation, which requires two parameters. Growth rate, how fast cells replicate, and colony diffusion coefficient, or cell diffusion, so how quickly a cell diffuses farther away from the point where it has spawned. Finally, we have the tab for the diffusion coefficient of all species in our system. In most cases, species will not be diffusible. So for example, in the repressilator, neither the mRNA nor the protein product can diffuse outside the cell, so we have 0 for all these species. Nevertheless, it is true that as cells diffuse in the simulation, they will carry with them all the intracellular components. So for all these intracellular components, we have checked the diffuses with colony box. We have a parameter light that does not diffuse with the colony because it's an external inducer and it is independent from the colony. We could also have some species, such as quorum sensing molecules, that diffuse outside of the cell. In that case, we can uncheck the diffuses with colony box and set the real diffusion coefficient. Make sure that the unit you choose matches with Ly length, or otherwise you can adjust it by leaving length dimensionless and dividing the diffusion coefficient by the square root of the physical length. Okay, we're ready to start our simulation. I will remove PN2 and PN3 from these settings because we want to compare with the pseudo 2D image we have generated before, and we run a simulation. You can now see two graphs. On the right, we have the colony growing, so basically the cell concentration at any given location, while on the left we have the concentration of the element we are interested in, PN1 in this case. The concentration of PN1 at any specific location is given by the intracellular concentration multiplied by the cell concentration at that location. As the simulation finishes, you can see this artistic pattern on the right image, and this is just due to the fact that there are small numerical variabilities as the entire colony exceeds 0.99. So basically this is all 0.99. And if we look at the pattern on the left, we see that it nicely matches what we obtain with the figure 2D pattern. We have a high peak, a low peak, high peak, low peak, and so on. And you notice that we were obtaining multiple plots as the simulation was evolving.